Thank you. Can you hear me? Is it working?
Yeah, this is only for the recording.
Okay, fine. Oh, all right. Okay. So before I start, let me thank Pratap for inviting me for this lecture. So I'm going to talk about disorder in quantum spin half chains. And before I start, let me just say a few words to put this the whole work into a perspective which is relevant to the contemporary condensed matter physics. So almost 3 decades back, Duncan Haldane had predicted, or conjectured rather, that the integral spin chains should have a gap in their spin excitation spectrum. On the other hand, the half integral spin chains should be gapless. Now, both these statements, that integral spins should be gapped and half integral spins should be gapless, are very intriguing. Before I go to the spin half case, let me say a few words about the spin 1 chain, which is the integral spin chain, where a gap is expected in the spin excitation spectrum. So apparently this gap, which is known as the Haldane gap, this gap is a consequence of a topological term in the effective Hamiltonian. So in that sense, the gap is topologically protected, probably in the same way as the surface states in a topological insulator are. And therefore, the disorder should not really have a great influence, at least a small amount of disorder should not affect the properties, or at least this gap, in a dramatic way. On the other hand, in the case of spin half chains, and in particular antiferromagnetic spin half chains, the properties can be rather sensitive to the presence of disorder in the chain. So I said in the beginning that the fact that a spin half chain has a gapless spin excitation spectrum is rather intriguing. And the reason for that is that if we look at the excitations of an antiferromagnetic spin half chain, then as k goes to 0, k being the momentum of the spin excitations. So that is that what I mean is, in the long wavelength limit, the dispersion goes to 0 linearly, almost linearly, and this we know is from the acoustic waves. We know very well that this is the property of long range ordered systems. But what is in fact very intriguing is that in antiferromagnetic spin half chains, there is no true static long range ordering. So despite the absence of a long range ordering, there is a linearly dispersing excitation spectrum, and the interest is to see how disorder will affect this fundamental property of antiferromagnetic spin half chain. So this is how I have structured my talk. So I am going to first introduce you to the materials. So the model systems on which the physics of antiferromagnetic spin half chains can be realized. Once that is done, then we will leave the materials aside, and of course the materials will be there in the background. Then we will go into the crux of the talk, which is about how the properties change when disorder is induced in the spin half chains. So I'll give a brief introduction, which will be mainly tailored towards students. So I'll talk about properties of spin half chains in their pristine form as well as in their disordered forms, and then I'll come to the results that we have obtained over last 4-5 years on these materials. So the model materials that I'm going to talk about today are these two cuprates, strontium 2 copper oxygen 3 and strontium copper oxygen 2, and soon I will show you the crystal structure of these materials. So here copper is the only magnetically active element, and copper is in a divalent state. So in the d orbital there are 9 electrons. So therefore copper 2 plus carries a spin half. So both of them have a spin half object in their formula unit, and the impurities that we are going to work with are zinc, nickel and cobalt, and these impurities are going to replace copper in the spin chain, and you will see the chain like structure in this slide. So here I have shown the structure of La2CuO4 because I thought this is something that most of you will be familiar with. So this is the parent compound of high temperature superconductors. Almost 3 decades back, Bednorz and Mueller hole doped it to get high temperature superconductivity, which started a whole new area in condensed matter physics. So the structure of this compound is actually consists of these copper oxygen planes. And within the plane, the blue balls here represents the copper atom and the brown one represents oxygen. So you can see that both along the A axis as well as along the B axis of the crystal, the copper spins can interact with each other via this intervening oxygen through the super exchange interaction. On the other hand, along the C axis, these planes, copper oxygen planes, are separated from each other by a buffer layer which consists of lanthanum and oxygen. So this non-magnetic buffer layer provides a magnetic isolation to these magnetic planes. So that's why this is a 2D, this is a canonical example of a 2D quantum magnet. Now we want to go from 2D to 1D, and we can do it chemically. So we will replace lanthanum by strontium. Lanthanum is a tri-positive ion. So if we replace it by strontium, which is divalent, then in order to maintain the charge neutrality of the formula unit, we will have to remove one oxygen from the formula unit. And when that is done, so these two oxygens, for instance, are missing now here, and similarly the oxygen from here are missing and here are missing. So what happens now is that the interactions are prevalent only along the p axis of the crystal, and along the a axis there is no super exchange path. So we have gone from 2D to 1D. So this is an example of a one-dimensional quantum magnet where the spins interact only along one crystallographic direction. Along the other crystallographic directions, either the super exchange paths are too extended or the super exchange path doesn't exist. So this is one of the compounds.
There was a structural change.
There is no structural change. I mean you can see that you can map everything else one to one in going from.
When you remove that one oxygen, is there not an elongation or contraction?
Of course, there will be. Yes.
The distance between the copper atoms along the a-axis now is extended, right?
I don't know the details, but definitely there will be changes in the lattice parameters. But the structure remains the same. So now we go from 213 to 112. So we reduce the strontium concentration, or in other words, we increase the copper to strontium ratio. The structure once again can be mapped onto the same structure, La2CuO4, except that now you have more copper atoms. So therefore, the chain is slightly extended. In fact, this is a zigzag chain. So you have copper sitting here as well as here. So these two copper atoms are interacting via this 90-degree bond angle. So that's the difference. So we are going to look at the properties of this compound as well as this compound. The properties are not very different because the ferromagnetic exchange between these two chains is rather weak compared to the interchain interaction. So therefore, the properties are essentially independent of the structure, except that at very low temperature, this ferromagnetic interaction starts showing up, and that gives rise to some sort of frustrated magnetism that you will see in a while from now, because there is a triangular array sitting here. So since we are interested in incorporating impurities in the material, we would like to see the response of these spin chains in the presence of impurities. We would not like to have unintended impurities going into or incorporating into the crystal structure. We would like to avoid anything that comes from outside. So in order to do that, one of the best ways of growing single crystals of these materials is using float zone method. And the obvious advantage of using floating zone technique is that as you can see here, there is no crucible required in growing single crystals of these materials. So in all these methods, you grow crystals from a melt, But in the first three methods, the melt is in contact with the crucible. You are holding the melt in a pot or in a crucible, and there's always a chance, because these crystals are grown at very high temperatures in excess of 1000 degrees. So there's always a chance of incorporating a small amount of flux material into the crystal. That can be completely avoided if one takes this route of growing these crystals by float zone technique. So this is how the float zone technique works. Basically, here is the floating zone, the molten zone, the melt, which is actually suspended or rather which is sandwiched between these two solids. So the lower one is the crystal which is being grown, and the upper one is the same material in the polycrystalline form. So you make rod of the material in the polycrystalline form, and you make a melt between them, and that's how the crystal grows. So all I wanted to show here is that the melt is nowhere in contact with any crucible material. So I'll not go into the details of the crystal growth, but I just wanted to show you that these three, there are three compounds in SRO-CO binary phase diagram: 213, which I already introduced you to you, and then 112, and then there's one more which has a slightly strange stoichiometry. It is strontium 14, copper 24, oxygen 41, and because of this strange stoichiometry, it is also referred to as telephone number compound. All these are examples of low dimensional systems, low dimensional magnets. Here you have linear chains, here you have zigzag chains. This compound has a hybrid structure consisting of chains and ladders, so we are not going to discuss this one here. These two, as you can see here, have melting behavior which is referred to as non-congruently melting. The reason is that if you start heating it up, then rather than going into a liquid state directly at a fixed temperature, it dissociates at a certain temperature which is known as the peritectic temperature. So it dissociates into a solid. So this T lines tells you in the components in which it dissociates to. So it dissociates into SRO as well as this liquid whose composition is gamma. And in order to get a stoichiometric melt, you need to heat it up to temperatures that are above this liquidus line. So in order to grow such crystals, one has to use a special technique, because you cannot grow these crystals from their own stoichiometric melt. So what is typically done is shown here. So let me first take the example of materials that melt congruently. So in such cases, the polycrystalline rod as well as the single crystal and the melt which is sandwiched between them has the same composition. The example, for instance, is holmium ferrite. This is an orthoferrite. So in this case, all you need to do is make two rods, bring them to the in the hot zone and melt and get the crystal growth going. On the other hand, in the case of non-congruently melting materials, you have to have a molten zone of composition gamma, where gamma corresponds to the peritectic point in the phase diagram. So if you ensure that, then under the steady state condition at the upper interface, strontium 2 copper oxygen 3 will dissociate in this fashion, and at the lower interface it will recombine or crystallize in this by the reverse equation, so that under a steady state condition the volume of the melt in the float zone remains unchanged. So this is how the crystals are grown for these materials.
How will you determine that you have gamma there?
Yeah, so that's a very tricky thing. So what we do is we start the growth by studying the phase diagram. We make a palette of composition gamma, and we melt this palette between the feed and the seed rod to start the growth. And then we have to fine tune the parameters, the growth parameters, to ensure that we get gamma. And to check whether you had gamma or not at the end of the growth, you can freeze the float zone, and then you can actually cut it and look at the composition of the.
Necessary to do the phase diagram of the.
Yes, if the phase diagram is known, things are much easier. But if it is not known, then one has to either determine the phase diagram or do some hit and trials. Sorry, the size of. Yeah. So. Yeah. So the size of the pallet, the weight of the pallet should match the weight of the float zone in the steady state condition. So, a priori it is difficult to tell what the weight of the pellet should be, but we take an approximate amount, all right, and then the crystal, once you start the crystal growth, the crystal does not start growing immediately. It needs some self adjustment, self corrections. So, these self corrections happen. So, what that means is that in the beginning you will not grow the correct phase. You might grow some secondary phases as well until the zone has corrected itself. Once that self correction has happened, then the crystal growth proceeds without any interruption. Gamma is not a phase. Gamma is just the composition of the melt that we will obtain once the material decomposes. So, in this case, for instance, the composition of gamma will be almost 60:40. If you are trying to grow strontium copper oxygen 2, it will decompose into this composition, having solid having this composition and a melt having this composition. So, this is the peritectic point on the phase diagram, and so by looking at the phase diagram you decide what the gamma should be.
I have a more basic question about this crystal growth process. So, you said something about how the float zone doesn't have a crucible, so you can grow very pure things.
Yeah.
But at this, when you start this process, do you
Yeah.
need to have a very high quality single crystal on the bottom side?
Not really. I mean,
You need some single crystal.
it's not needed actually. So, one can start with a polycrystalline seed instead of a single crystal. Then what's going to happen is that as the growth proceeds, one of the favorably aligned grain is going to grow and it will supersede the growth of other grains. So, eventually after few centimeter of crystal growth, you will be left with a single crystal one.